Okay, yeah, thanks, Maddie, for the invitation. It's really my pleasure to be here. I've been following this seminar for a while, so very happy to finally present. And also, hi everyone. My name is Bo. I'm a PhD student. I'm a final year PhD student at the University of Toronto. So very excited to be here to talk about this paper we recently wrote. The title is Conformal Inverse Optimization. I wrote this with Tim Chen, who's my supervisor at University of Toronto, and also Professor Eric Delage, who is at the HEC Montreal. Okay. So I guess this talk will be a little bit different from previous talk that have appeared in this channel, because I'm not trying to propose a new conformal prediction method. Really, I'm trying to motivate a conformal prediction problem in the context of human-AI interaction. And then I'm going to combine conformal prediction with some optimization idea to tackle some of the challenges we have there. Okay. So also, this is still ongoing, so any feedback questions will be very helpful, and feel free to just unmute yourself during the presentation. I'll be happy to engage right away. Okay, so without further ado, let me start with a little bit intro to the motivation of this work. Okay, so I became interested in this problem because of, I guess, very common phenomenon in ride sharing, and I think most of us have seen this when using Uber or Lyft. Right? So we know that rideshare drivers don't always follow the path recommendations they get. So for me personally, as a rider, I didn't really think that's a big issue, because drivers usually know the city very well, and usually they can find a better path, and I'm willing to follow that. However, when I was talking to a friend who worked as the data scientist as one of this big ride-sharing company, what I learned is that as a platform, they don't really like this kind of deviation, and there are two main reasons behind. Right, so first of all, this is going to affect rider experience. It's for sure going to cause some confusions for the rider and sometimes even safety concerns. Imagine that you take an Uber home at midnight and your driver suddenly deviates into a very sketchy neighborhood. He may tell you that, oh, I'm taking a shortcut, but still it can be very scary, at least for some people. And on the other hand, this is going to create operational uncertainties that affect the efficiency of many downstream problems. Right, so for example, there are hundreds of data scientists working very hard trying to estimate the arrival time, price the trip, or even match the drivers and riders together, assuming that the driver will follow this path recommendation, because this kind of route is an important input to all these algorithms, and they have to decide that before the driver even accepts the invitation to this trip. Right? So I became interested in this problem, and I did a little bit more research online. What I found here is it's actually a very common phenomenon, not just in ride sharing. And in the literature, people usually call this algorithm aversion, meaning that these days algorithms can perform very well, usually much better than human, but we human beings are often reluctant to adopt these recommendations for many different reasons. So we have seen this in ride sharing, as I introduced earlier, in last mile delivery in a very similar way. And just as one more example to show you that this can indeed be costly in practice. In this retail operations paper, the author did a field experiment where they used this kind of data-driven product assortment algorithms to decide what kind of products to display in some offline retail stores. And what they found here is that this kind of algorithm recommendations are overridden quite often, over half of the time in practice, leading to an almost 6% reduction in profits. So indeed, this can lead to non-trivial economic loss. A very natural question arises here is, if algorithms are so good, then why are people averse to them? There's a growing body of empirical research on this topic. So, for example, sometimes there are some transparency or interpretability issues. This is particularly important when we use those black box models in some high-stakes settings, for example, healthcare. And sometimes people don't like algorithms because they had bad experiences before. And I'm not going to read a list, and this is by no means comprehensive, but I do think this is a very important research question, because once we understand all these reasons, we can start thinking about what levers we can apply to mitigate algorithm aversion. And this is what we're going to do in this paper. So we're going to focus on the first reason on this list, which is the misalignment between my algorithms and my human intuition. Right, so this is particularly relevant in routing and also last mile delivery settings, because drivers usually deviate from the recommendation because they don't believe the given path is good. They have a better idea in mind. And actually, this is not just in ride sharing. Me personally, I do this a lot as well. So essentially the research question we're looking at here is how do we generate some decision recommendations that are first high quality and second intuitive, meaning that they are perceived to be high quality by most people, so they're more likely to be adopted. And the key challenge here is how do we even quantify human perception? If we ask a driver to tell us about her intuition, most likely the response is I don't know, because intuition is not something, we definitely have it, but it's not something we can easily describe or communicate. So in this paper, instead, I'm going to look at how people made decisions in the past, and hopefully I can learn something useful from that. Okay. And so as a preview of our method and I guess also contributions, in this paper, we assume that we have access to some decision data in the form of a feasible region and the decision pairs, right? So which options people were considering in this feasible region and which one they finally picked. And based on this kind of data, I'm going to construct an uncertainty set that contains most people's perception of the problem regarding how they evaluate all these different options. Right? So given this uncertainty set, in the future, when a new set of options or new feasible region comes in, I'm going to solve a robust optimization model to provide a recommendation. So for those who are not very familiar with robust optimization, you can think of this as a bi-level game that involves two different players. So we are player one in this game, and our goal is we want to pick one option from this feasible region as our recommendation. Right? And then given this recommendation, there's another player, player two, who is trying to find a perception in this uncertainty set to make my recommendation as bad as possible by solving this maximization problem to maximize the cost incurred by my recommendation. Okay. And our goal as player one in this game is we want to minimize this worst case outcome that can possibly happen in practice. And another way to think about this is a process to find a recommendation X that is perceived to be good by most people covered by this uncertainty set. And hopefully this helps to align my recommendation and human perception.
Sorry, can I ask a question here?
Sure. Yeah.
So I'm trying to connect this slide with the previous example that you had, ride sharing. In the context of ride sharing, what would be the feasible region and what would be the observed decisions? Observed decision, I think it's easy, the path that was followed.
Yeah.
But how will you get the feasible region?
So yeah, that's a great point. And actually it's coming up in the next slides, but in short, you can think of feasible region, like for example, you're going from point A to point B, you can think of the feasible region as all possible paths from A to B. So that's all the options that people are considering.
So basically the assumption behind that is that the driver in his head has considered all the paths, all the possible paths.
Yes, exactly. Yeah.
Okay.
Yeah, that's a good question. Okay, so that's the high-level framework. I'll go into the details later in the presentation. But in terms of contribution, I think this is the first approach that converts this kind of decision data to uncertainty sets. I think this will be more clear later, but in order to apply existing approaches to construct this kind of uncertainty sets, we always need some observation of human perception, but we never really observe human perception in practice. So all the existing approaches don't apply, and we need some new method along this direction. And I'll also show you today that our entire pipeline have pretty good empirical performance and also have some theoretical guarantees on solution quality. Okay. So yeah, that's the high-level picture. And next, I'm going to formally set up the problem for you. Okay. So in this paper, we assume that when making a decision, people solve an optimization problem in their mind. And throughout the presentation, I'll use this shortest path problem as an example. But our method is actually way more general than this. Okay. So imagine that this is the road network in the city that you live in. I'll talk about Toronto because this is where I live in. Okay. And lots of people, all of us, drive on this road network. Okay. So for each of us, there's a feasible region. And as I mentioned earlier, this feasible region corresponds to a origin and destination pair. Right? There are two locations, and this capital X contains all the possible paths going from O to D. We assume people consider all these different options. Okay. And in the objective function, there are some parameters denoted by theta. Right, so you can think of this as the real travel time on each row segment, and people are trying to minimize the travel time here. Right, and the real travel time is usually not accessible to our decision makers. So our drivers relies on their perception, denoted by theta hat in this optimization problem. So you can think of this theta hat as the perceived travel cost on each row segment, and this is a noisy perception of this ground truth information. Okay. And we solve this optimization problem. We get a final decision denoted by x hat, which is the path from O to D. Okay. And as I mentioned earlier, it's very difficult to read people's mind in practice, so we never really observe this intuition. But it's very easy for us to see the origin and destination of a trip, which correspond to this feasible region, and also the final path taken by our driver. Okay. And of course, there could be many drivers on this network, so we can potentially access many feasible region and decision pair. And our goal here is using this decision data sets, I'm going to construct a policy pi. So going forward, when a new origin destination pair comes in, or new set of options comes in, I'll use this policy to pick one solution from the set as my recommendation to people. Okay, I'm gonna pause for a few seconds in case there's any question.
Yeah, I have one question. So in this example that you are showing, we have 3 drivers. Is the feasible region the same for all of them?
They're different because, for example, this guy is going from O to D, and this guy is going from this point to that point.
Oh, right. So, okay, right.
Yeah, shadow paths can be different. Yeah, but that's a good point. Yeah.
Okay. But yeah, obviously, if the start and end points are the same, then the feasible region is also the same.
Yeah. So they can have different feasible regions, but they share similar, like they can use the same perception regarding this network to solve their problem, although their problem can be a little bit different. Okay, so this is our goal. We're gonna learn some decision policy. And to get a good decision policy, I think the first order thing we should agree on is how do we evaluate these policies, right? And for this purpose, I'm going to propose 2 evaluation metrics, one objective and one subjective. Okay, so for the objective one, I call this actual optimality gap, or AOG. So essentially, we assume that there are some ground truth parameters that we usually have no access to. Again, you can think of this as the real travel time on each row segment. So the first term here is essentially the travel time achieved by our recommendation, pi x. And the second term here is the best travel time we can possibly achieve in hindsight if we have access to this theta star. So this is the performance gap between our policy and the best possible policy if we have access to this theta star. And we take expectation over the random feasible region because origin destination pairs can randomly pop up in the city, and we focus on the case where we use one policy to provide the recommendation for everybody.
Sorry, one other question here. So is looking into the second term inside the brackets makes me think that the travel time is theta times x. Is that correct?
Exactly, yeah. So you can think of this x as a vector that have the same dimension as the number of row segments in the city. And if the entry is 1, it means that this row segment is used, right? And then this theta has the same dimensionality and it's the travel time along each row segment. So this is basically
is the travel time theta or theta times x?
The travel time, so this theta is the travel time on each row segment, and theta times x is the travel time along my routes or paths.
Oh, okay, I see. Got it. Got it.
Okay.
Each row segment. Okay.
Yeah.
And therefore, the first theta is the real travel time on each segment.
Yes, a theta star represents that on each row segment. But when we multiply this with my recommendation, this is the travel time I achieve along my path. Okay.
Okay, thank you.
Okay. So that's the objective metric with respect to this ground truth information. And the second metric is subjective. Right? So the formula looks very similar. The only difference here is instead of using this ground truth information, I'm going to use human perception to evaluate my policy. So again, this is the perception of the travel cost on each row segment. And if we multiply this with my recommendation, this is the travel time, the perceived travel cost incurred by my recommendation. Okay, and this is the gap between what we achieve and the best possible thing we can achieve if we know human perception. Okay. And also we take expectation over the feasible region and also human perception here. Okay. So conceptually, you can think of AOG as a measure of how good my recommendation actually is, and POG as a measure of how good people think my recommendation is. Right? And as you can imagine, these two things may or may not align with each other. We don't know. But our goal here is we want a policy pie that has low AOG and low POG simultaneously, meaning that we can recommend something that is actually good and people think they are good, so they are more likely to be adopted. Okay. So that's the goal. And how we do that? In the literature, a very natural idea commonly used is called estimate then optimize. The idea being we can first get a point estimation of those unknown parameters in the objective function, the travel cost on each row segment, based on my decision data. And once I have this estimation, going forward, when the new feasible region comes in, I simply solve that optimization problem to provide a recommendation. Right. So the second step here is relatively easy because I simply just solve the optimization problem I specified. There are lots of software we can use to do that. But the first step here is a little bit tricky because I'm trying to estimate something that I never really observe. Right? The thing we are trying to estimate is the human perception, but we observe are some decision corresponding to this perception. Right? It's a little bit tricky. So in the paper, in the literature, what people usually do is to leverage something, a special technique called inverse optimization. Right? So I won't go into detail, but at a high level, we have access to this kind of decision data, right, in the form of the historical decision we see and the feasible region that people were considering. And we're going to solve this empirical risk minimization problem. The decision variable here is the cost vector that I'm trying to estimate. And the goal here is we want to minimize this loss function that measures the suboptimality of my decision under my estimation theta. So if we can find a theta that make my historical observation optimal, then this loss will be zero. Right. So conceptually, I'm looking for one cost vector, the perceived travel cost on each row segment, that can make all my historical decisions as optimal as possible. So that's the high-level idea of inverse. I won't go into detail, but the point here is there are lots of existing algorithms we can leverage to get this kind of point estimation, although the task is a little bit tricky. Is there any question about inverse optimization?
No, I'm good. I'm good.
Okay, nice. So that's the idea of inverse. So we can definitely make this pipeline work, but since I'm only, I guess, 20 minutes into the presentation, this is not the end of the story. So as I'll show you later in the numerical experiments, this pipeline doesn't perform very well in terms of the AOG or POG metrics we defined earlier. The key reason here is that our setting is a little bit different from the traditional inverse optimization setting that we talk about in the literature. So in the traditional setting, this kind of decision data are usually generated by some experts. Right? So for example, there are delivery truck drivers who have been in the business for decades. Right? And those drivers usually have very similar perception of the road network. And in this case, it makes sense to get a point estimation to represent my entire data sets, and it carries some expert knowledge. Right? However, in our setting, our decision makers are not necessarily experts. Some of them may be, but some of them are gig workers who work on a part-time basis. Some of them even just drive for fun, right? And they're human with preferences. And my preference can be very different from yours. There's potentially a very wide distribution. And in this case, if we get a point estimation, it doesn't make sense because first, it doesn't carry expert knowledge. And second, it's not representative of my data sets. There's probably no consensus at all in my data sets. Right. And based on this kind of high-level intuition, we were able to show some negative results regarding this pipeline. So we show that in our setting, if we apply the existing approaches, then we can achieve arbitrarily large AOG and POG simultaneously, meaning that our recommendations can be low quality and misaligned with human perception, so they're very unlikely to be adopted. Okay. So that's the challenge. And based on this observation, I'm going to propose a new pipeline. The key difference here is instead of getting a point estimation in the first step, I'm going to construct an uncertainty set that contains most people's perception about the problem. Right? And as I mentioned earlier, I'm going to, based on this uncertainty set, I'll solve this robust model to provide a recommendation given this uncertainty set. And again, you can think of this as a process to find a option in my feasible set that is perceived to be good by most people captured in this uncertainty set. And again, the second step is relatively straightforward. We simply solve this robust model. It's slightly more difficult than the previous one, but there are lots of algorithms we can leverage. What's really tricky here is the first step, because we're trying to estimate something we never really observe. And I think this has never been done in the literature. So to see why this is challenging, I'm going to show you how we usually do this in the literature. So in the literature, when we talk about constructing an uncertainty set, what we usually need are some observations of these unknown parameters, right? And then based on this kind of empirical distribution, I can construct a set, for example, an ellipsoid in this example that covers a fraction of my support, right? So that's how people usually do it. But again, as I mentioned, we don't really observe this theta hat in our setting because they are human perception. What we observe are some decisions that people generate based on their perception. Okay, so in order to apply the existing approaches, the key question we have to answer here is then, is it possible to recover human intuition based on their decision? Okay. And unfortunately, the answer is no in this case, and I'll show you an example to see why. Okay, so imagine that this is the feasible region that's constituted by people. They can pick any point in this feasible region as their decision, right? And this blue circle represents the decision we observe from this decision maker. Right. Assuming that this person is solving a maximization problem, then when we solve this inverse problem to recover the intuition, we are looking for a cost vector that can make this observation the extreme point along this direction that the cost vector is pointing to. Okay, so it's very easy to verify that this cost vector actually satisfies this condition. So under this cost vector, this decision is indeed optimal to the optimization problem we specified. However, this kind of solution is not unique. It's easy to verify that all these cost vectors that lie in this purple region can make this decision optimal. Right. So hopefully this example convinces you that there's no one-to-one correspondence between human decision and the human perception. So there usually exists multiple perceptions that can explain my observation.
Sorry, is the underlying reason for this what you just mentioned, meaning that you can have single decisions, a given decision correspond to two different perceptions?
Yes. So there could be multiple possible perceptions that can explain what I observe. So there's no one-to-one correspondence. That's the point. Yeah.
In other words, perception is not a function of the final decisions, but the other way around.
Yeah, decision is a function of perception.
Yeah,
exactly.
Okay.
Yeah.
And when the decision is function of the perception, obviously you may not be able to recover perception from the decision.
Exactly. Yeah, you're getting it right. Yeah. Okay, so we have this fundamental identifiability challenge. So it's very difficult to characterize the empirical distribution of my human perception based on the decision data we have access to. Okay, so that's why it's very difficult to apply existing approaches. And this is where conformal prediction comes in. So interestingly, I think the machine learning community has a very similar challenge as we do here, right? So when people use this kind of black box machine learning model to predict some targets, sometimes it's insufficient to just provide a point prediction. Sometimes we want to construct this kind of interval prediction that contains the true target with high probability. Right? So for example, here I'm trying to predict the arrival time of a trip based on some contextual features. And the most straightforward way to do this task is I first predict a distribution, and then I can naturally construct an interval by picking some quantiles here. Right? But because of the black box in the middle, it's usually very difficult to construct this kind of distribution prediction. And I guess for this audience, I don't have to talk too much about the motivation, but recently there's an idea called conformal prediction, originating from the statistical literature that can do this job very elegantly. So there are a whole bunch of methods we can use to construct this interval that contains a true target with high probability without characterizing this distribution in the first place. Okay. So just to link back to the problem that I described earlier, in this pipeline, if you think of this black box model as my inverse optimization problem, and the features as my decision, and the human perception as my final prediction targets, then we can probably borrow some conformal prediction idea to construct this uncertainty set, right? Because for this uncertainty set, we have a similar requirement. We want it to contain something, the next human perception with high probability, right? So that's how we build the connection. Although I don't think this is a trivial extension because there are some optimization structure in this black box that we have to consider. And we're not trying to estimate a single value. We're trying to estimate a potentially high dimensional cost vector. Right, but I think the main the main connection is here. Okay. Any questions? Nice. Okay.
All good. All good.
So that's the connection. And next, I'm going to show you how we do it. Okay. So because of the connection to conformal prediction, I'm going to call this method conformal inverse optimization. So we're going to do this in 3 steps. Right, so first of all, given this decision data set, I'll split it into 2 parts, right, training and validation. So for the training parts, I'm going to apply the existing inverse optimization method to get a point estimation. Right? And next, I'll combine this point estimation with my validation set to calibrate an uncertainty set around my point estimation. Right? So for those who are familiar with conformal prediction, this is really split conformal using some technical terms. There are alternatives in the literature, but we choose this because of mostly because of computational trackability. So the only thing new here is this calibration step, and I'll focus on this for the rest of the talk. So in this paper, we focus on the specific type of optimization problem. So we assume that in this objective function, this objective is linear in the parameter that we are trying to estimate. Right, so this includes many different problems, including linear programming, multi-objective optimization problems. So there could be lots of different applications. And based on this kind of structure, it's easy to see that the solution to this optimization problem is invariant to the scale of theta, meaning that if I multiply theta with the positive constant, the optimal solution wouldn't change. So we don't have to worry about the magnitude of human perception. We only care about the angle, really. So because of this observation, we are going to construct our uncertainty sets in a very specific way. So here we have this L2 constraint saying that all the human perception should be on the unit sphere according to the L2 norm. Because according to this structure, we don't have to worry about the magnitude, right? We only care about angles. And we have this cosine constraint, which essentially saying that my uncertainty set should centered around my point estimation I get from the previous step. And this alpha essentially specifies the max angle between my point estimation and any other cost vectors in my uncertainty set. Okay. So essentially, this alpha specifies the size of this set. And this is the only parameter that we have to calibrate using my validation set. Okay.
Sorry, a question if I may. So you previously mentioned that theta in the ride sharing example is the travel time for each, is the perceived or estimated
travel time.
Perceived travel time for each segment.
Yes.
Okay. And now I'm trying to understand this constraint that you put on L2 norm. What does that mean?
Oh,
what does it mean, the perceived travel times?
Yeah. So I would say, so I think when we enforce this L2 norm constraint, the value doesn't really care, like the value as different entry of this vector doesn't carry any actual meaning anymore, but the relative relationship between them still carries a meaning, right? For example, if the value for this row segment is higher than that one, it means that the travel time along this one is higher. Right? So my shortest path wouldn't change if I multiply the travel time on each row segment by 2 or 3, right? The solution would still be the same. So the magnitude of this value doesn't really matter. What we care about is the comparison between different row segments, if that makes sense.
When you say multiplying this data by a constant, does that mean multiplying the perceived time for different segments by the same amount? Or does it also include multiplying the perceived time for like 2 different segments by 2 different amounts?
It's by the same amount. So
by
if we try everything by the
obviously.
same amount, then things wouldn't change. Right? The optimal path was still exactly the same.
Sure. Okay.
Yeah. Okay. Yeah. Thanks for the question. That's a very good one. It's good to clarify things here. Any other questions?
No, I'm good for now. Thank you.
Okay. So this alpha is what we have to calibrate based on the decision data set. Okay. So how we do this is we're going to solve another optimization problem. Sorry, there are lots of optimization problems today. So the decision variables here, of course, include this size of my uncertainty set alpha that we have to calibrate. And in addition to that, I'm going to take a guess for everybody's intuition in my validation set. So I denote this by theta k. So k is the index of different decision makers. Okay. And the goal of this calibration problem is to minimize the size of my uncertainty set. Right. This is similar to other conformal prediction problems where we try to minimize the size of the interval because I want this set to be efficient. Right. And in the constraints, I have to make sure that my human perception theta k can indeed make the corresponding optimization problem optimal, because that's the definition of human perception in our setting. We also make sure that everything is on the unit sphere because of the scale invariant thing that we discussed just now. And finally, we have this constraint saying that my uncertainty set should cover gamma % of my validation of perceptions in my validation set, right? So really, this gamma is the usual hyperparameter appear in conformal prediction. This is something we have to tune. We can set it to maybe 70% or 90%, right? So yeah, that's I think very similar to the conformal prediction problems. And it turns out that if we calibrate the uncertainty set in this way, our set is still valid out of sample. So here are some, I guess, standard conformal prediction results. So with some standard IID assumption, we can show that with the probability at least gamma, this is a percentage we specified earlier. For the next unsynced decision, there exists one cost vector in my uncertainty set that can make his decision optimal. So that person, although we haven't observed so far, his perception have some representation in my uncertainty set. Okay. And we further show that this coverage guarantee can converge to this target level asymptotically as we increase the size of my validation sets. Okay. So essentially, this is saying that I can always achieve the coverage level out of sample as I specified, and as I use the larger and larger data sets, I don't overcover too much. And
sorry, one question here. This coverage that we are talking about here, is it conditional coverage or is it the marginal coverage? Meaning that is it for a fixed calibration or in your example, fixed validation set?
This is marginal. Like
this is the marginal. Okay.
Yeah.
And then with conformal prediction, this marginal coverage is valid even when n, the size of the validation set, is small.
It's small, yeah, but for small n, there are some coverage things that we cannot achieve, right? So for example, when n is equal to 2, we can only cover like under 50%. There are some lighter things, yeah.
Okay.
Yeah, that's a great point.
Oh, right. Sorry, I misread the second equation here.
Yeah.
Okay. Here you are fixing. So that's the second equality. The second equation inequality is telling that for us to be able to reach the requested gamma, n has to be high. Is that what the second equality is telling us?
Yeah. So when I have a huge validation set, the probability at least Oh, I think this is one minus, oh, this is a typo here. So this is a 1 minus 1 over n. So this thing will go to 1 with the probability 1. And then this term will go to 0. So we achieve the exact coverage as we want.
Okay.
Okay.
All right. Thank you.
Yeah. So and furthermore, other some very mild technical assumption that I won't talk about today. We can relate this coverage result to this performance guarantee. Or we can show that if we use this uncertainty set to provide recommendation, we can achieve upper bounded AOG, POG simultaneously, meaning that we can provide good recommendation and they are perceived to be good. Okay. So yeah, that's a high-level summary of the method and also computational, some theoretical results. And next, I'll go to show you some computational results to show the performance. Okay. So again, I'm going to use the shortest path problem as an example. And you can, again, think of this as the road network in the city you live in. And on this network, I'm going to generate 1,000 different drivers. Right? So again, this network have some ground truth information that we don't have access to. That's the real travel time on each row segment. I'll use this to calculate the AOG of different policies. Right? And for each driver, there's a random origin destination pair. They could be different from each other, but they share the same network. So their perception about the network is transferable between different drivers. Okay. And they have a random perception, theta k. It's a noisy perception of theta star. This epsilon term is from some random distribution. And we use this to calculate the POG. Okay. So we get a path from each driver by solving a shortest path problem based on his origin destination pair and also his perception. And this kind of path will be used as the data sets in my computational experiments. Okay. Okay, so in this figure, I'm showing you the percentage reduction in out-of-sample POG achieved by our method compared to the inverse optimization approach that used in the literature. Okay, so here I'm showing you that when I set the coverage level to 10%, I can improve the out-of-sample POG by roughly, I guess, 15%, which is great. And by the way, we have some variance here because we repeat experiments with different data splits. Every time the results can be different, but we are consistently better. So this is the 95% confidence interval. Okay. And as I try different coverage level, the results can be different. It becomes better at the very beginning and then drop a little bit in the end. Okay. The intuition here is that if I set coverage level to a large value, say 99%, then I'm trying to consider everybody in my uncertainty set. I'm trying to hedge against the possible perception from everybody. This might be a little bit too conservative because at the end of the day, we're trying to average out over the whole population. So that's why the performance can become a little bit worse in the end. So I guess my takeaway here is that this gamma is a very important hyperparameter we have to tune in practice. And we can do this by some standard cross-validation techniques. But if you are lazy like me, it's also fine. Usually setting this to a relatively large value, like 70%, give us decent performance.
Okay. So this is the vertical axis is really the reduction in POG, yeah. Meaning that regardless of the value of gamma, this method, conformal inverse optimization, will always outperform the regular inverse optimization.
Yeah, empirically, this is what we see. We always have some benefit, but the size of
always right. Okay, so there's always some benefit.
Yeah.
Okay.
Yeah. And yeah, so that's about POG. And we also look at AOG of the policies. And I think and again, this is the improvement over the existing approaches. So we have very similar observation, which is a little bit surprising, to be honest, because remember that we learn from human decision data. And we assume that humans have no idea about the ground truth. But here I'm showing you that I can also improve the performance with respect to the ground truth, which is surprising. So the key reason here is that the point estimation in the traditional inverse pipeline, it doesn't really converge to the ground truth, even if we assume that the average perception across the whole population is equal to the ground truth, right? It still doesn't converge to that. And in statistical terms, this means that the inverse optimization is not a consistent estimator of the cost vector in my objective function. So that's why the traditional approach can be very off in terms of AOG. Right. And when I consider an uncertainty set with some probability, my uncertainty set will contain that ground truth. So that's why we can see some improvement here. So that's about shortest path. And if you are familiar with optimization, you know that the shortest path problem is a simple continuous linear programming problem, which is relatively easy. But our method actually also works for integer programs, which is actually way harder, especially when we talk about inverse problems. So we have some results about knapsack. I won't go into the details, but we have very similar performance here. Actually, the performance gap is even larger compared to the previous one. And I want to spend some time to talk about a very important decision we have to make in this pipeline, which is given a fixed data set, how should I split my data into training and validation for point estimation and calibration? Because intuitively, both steps can benefit from more data. But in practice, I always have to strike a balance to achieve the best out of sample performance. Okay, so we did a little bit more experiments here. So here in the x-axis, I'm showing you the size of my entire data set. Right? And the y-axis represents the percentage I put in the validation for uncertainty set calibration. Right? And the number here represents the percentage improvements we can achieve compared to the existing approaches. Right, so here, for example, in this cell, this is saying that I have a data set of size 160. I use 80% of them as my validation set, and my method is 13% worse than the existing approach in terms of AOG. And this is for POG in a very similar way. Okay. So I guess the takeaway here is very clear. If we have a very small data set shown by these two columns on the left-hand side, then don't worry about our approach, because we don't have enough data points to get good point prediction and good validation sets simultaneously. Right? However, if we have access to a relatively larger data sets, then we generally does better. And also we can generally benefit from putting more data points in the validation set. And I think this echoes our theoretical analysis, which requires the size of my validation set to go to infinity in order to achieve a good coverage out of sample. Okay. Okay, so is there any question about this?
No, I'm good.
Okay. So that's about the computational part. They're all based on synthetic data, which is great. It gives us lots of insights regarding how the model works and also how to make these important decisions in the pipeline. But eventually, our goal is we want to make some real-world impact. Right? We want to demonstrate our performance in the real application. So next, I'm going to talk about a case study that we recently put together regarding how to provide route recommendations for food delivery couriers on bikes. Right? We choose this application because lots of food delivery platforms, for example, DoorDash or Uber, they have been promoting this bike delivery for quite a while because there are lots of potential benefits. Right? It's physically active, we can make money and do workouts simultaneously. So one stone, two birds. And less maintenance, we don't have to worry about energy prices, less traffic conditions, and less time spending on parking. So it's actually way faster than car delivery in downtown area in Toronto, for example. And it's climate friendly. So this is what we care more and more about as a society, because we want to hit carbon neutral by 2050. Okay. And because of all these benefits, bike delivery is taking off in Toronto. So this is some pictures I got from some local newspaper. This is showing that lots of couriers who live around Toronto, they bring their bikes on the local train transit and commuting to downtown area to provide food delivery services. And there are so many cars that this train passengers start to complain about it. I guess this is some evidence showing that it's really popular now. So what are people thinking about when we talk about bike delivery? I guess on the platform side, the goal is very clear, right? We want to minimize the delivery time, because that's directly tied to how much money they can make, how many orders they can complete every day. And also that's a very important measure of service quality. Okay, so this is AOG in our setting. And on the courier side, I would say delivery time is still very important, but it doesn't usually tell the full story because, there are many other factors that can affect the routing behavior. For example, whether or not we have the right cycling infrastructure along the way to protect the couriers from the motor traffic things, right? And also, how's the traffic conditions along the way? Empirically, we usually see that the path actually taken by our couriers are usually very different from the the theoretical shortest path. We have seen this so many times in the literature, right? And As I mentioned earlier, this kind of deviation can create operational uncertainty that affects all these different decisions. For example, arrival time estimation, the batching of different orders, their assignments to different couriers. All of these requires inputs all of this requires the courier route as an input, and we have to model this before the couriers accept this order. Okay, so our goal here is we want a recommendation that has low delivery time, so we maintain some level of service quality, and we want these couriers to adopt our recommendation so we can improve the efficiency of all these tasks. Okay, and we're going to focus on this. The food delivery trips happened in this green area around the University of Toronto campus, and also this is where I used to live in. The blue dots are the real restaurants in this area we got from OpenStreetMap, and the customers, these orange dots are some residential buildings in this area. Okay, and just to be clear, we don't have access to real delivery trips, and if anybody in the audience have access to that, and if you are willing to share, please reach out. We are desperately looking for that. But for now, we don't have access to that, so we're going to generate some delivery trips based on some behavior model we have. Right. So for each trip, I'm going to pick one restaurant and one customer as an origin and the destination respectively. So we make sure that they're at least 1 kilometer away from each other, so we can justify using food delivery services in this case. And this trip is completed by a random courier with a random perception of this road network. And this time, instead of generating random numbers, I'm going to generate the perceived travel cost on each row segment based on all these different features, right? And this linear model is proposed in this 2017 paper. Okay, so the travel cost can depend on the distance, the time, the traffic volume, and also a measure of bike friendliness, which consider many other different things, for example, cycling infrastructure. Okay, so we have detailed row segment level data for these features. They are real, but we don't have access to this beta. So I'm going to randomly generate them from some normal distribution. And the mean of this distribution is estimated by this 2017 paper using some real travel behavior data in another North American city. So it's not perfect, but I think it's way more realistic than what we did in the computational experiments. Okay. So once we have this cost vector, again, I can solve the shortest path problem to get a roots. And this roots will be my data sets in this case study. And according to this data generation process, I'm going to formulate the forward problem that we assume the couriers are solving as this multi-objective shortest path problem. So the couriers are trying to minimize a weighted sum of all these different objectives regarding the travel distance, time, traffic volume, and bike friendliness. Okay, and we have access to all these features. So for any path, we can calculate these different objectives. But what we have to estimate here is this beta, which reflects the personal preferences for the couriers. Okay, and we can apply inverse optimization traditional approach to get a point estimation, or apply our approach to get a uncertainty set for this, and we can use them to prescribe future decisions. Okay, so the first thing we look into in this case study is about the trade-off between AOG and POG. As I mentioned earlier, AOG is the travel time, and POG is the perceived travel cost. And in practice, these two are usually different. And we want to see the trade-off. Right? And to quantify this trade-off, I'm going to add this constraint to my optimization problem when I make a future recommendation. So this is saying that my travel time achieved by my recommendation should be upper bounded by the best possible travel time times 1 plus epsilon. Okay. So here, this epsilon is a tolerance for travel time increase. If I set it to 0, then we have to make the shortest path recommendation. And as I increase the epsilon, I have a larger feasible region to operate. Then we can better tailor my recommendation to courier preferences, but you should expect the travel time to go up as well. Okay. So in this picture, y-axis is the POG, x-axis is the AOG. Both of them are out of sample, right? And this green square represents the shortest path policy, right? This is when I set epsilon to 0, and AOG will be 0 because I have to make the shortest path recommendation, but POG can be high because this is different from what couriers think most of the time. Okay. And as I change the value of epsilon, these are the curves I got for my approach in green and the baseline inverse approach in blue. So our first observation here is very positive. we see that using our approach, we can reduce this POG by over 90%, but only increase the travel time by 8%, right? So in Toronto, when we talk about delivery time, it's usually like 30 or 40 minutes. So that means I only increase the travel time by 2 or 3 minutes, which I believe most people don't care, but I can largely improve the alignment of my recommendation to courier perception, and this will significantly improve the operational efficiency of many downstream problems. Okay. And compared to the traditional inverse pipeline, when we target a specific POG reduction level, we can usually incur shorter delivery time, meaning that we offer a better trade-off between these two targets. Okay.
Sorry, one question. Why does POG always decrease as AOG increases?
So in the optimization problem we solve to recommend the future decision, the objective is to maximize the perceived is to minimize the perceived travel time, right? Your preferences. So as I increase epsilon, I should be able to do better in general. So that's why POG is going down. But at the same time, I might incur higher travel time. Does it make sense?
So for the two, when you change, so different dots in this plot, different squares, they correspond to different epsilons?
Yeah, they correspond to different epsilons. I increase it from 0 to 20%.
Okay, from 0 to 20%.
So here's 0.
Okay.
And here's 20%. Yeah.
So I will have to watch this part again. So please continue. I will have to watch it again.
Sure. Okay. Okay, so that's our first finding. We can offer better trade-off. And in the second experiment, I'm going to look at a fundamental challenge that we have to think about for any inverse optimization problem. Right, so to apply any inverse optimization technique, we always have to specify an optimization problem that people solve in their mind. But in practice, it's very difficult to verify this and even justify, right? And in fact, it's very likely that what we specified is wrong. It's not the real problem that people are solving. So it's very important to look at the model performance under this kind of model misspecification situation. Okay. So what we do here is when we generate the trip data, when we generate those perceived travel costs, we take this linear function to the power of delta, right? So when I set delta to values larger than 1, the perceived travel costs can depend on higher order interactions between all these different features. But when I solve the inverse problem, I always assume this delta is equal to 1. We assume the relationship is linear, right? So there could be some discrepancy between the data generation process and the model we specify. Okay. So we vary the value of delta and then repeat the experiments we have in the previous slides to see the trade-off between them. So we see that when the model is like misspecified, meaning that the delta is larger than 1, we generally achieve worse performance. It's more and more difficult to improve the alignment between my recommendation and the courier perception. So all these curves move up. Right? But when we look at the performance gap between our approach and the traditional inverse approach, we see that the performance gap becomes larger and larger as we increase the value of delta. Right? So this is showing that our model is more robust to model misspecification in this setting. Okay, and finally, I'm going to look at personalization. Right, so far, we focus on the case where we have one model to make recommendation for everybody. But when I talk about this with friends and also present this at conferences, a very frequent question I get is, if we are collecting personal data, then why don't we do some personalization? Because intuitively, that should give us the biggest improvement in terms of decision alignment. Right? So we did that. We add a new baseline in this figure, PIO, which means I get one inverse optimization problem for each person using his own travel behavior data. Okay, and I vary this variable n trips, which is the number of data points I collect from each courier. Right? So we see that in this data pool regime, our method is in general much better than the personalization strategy, because we can quickly benefit from the huge data set we can aggregate across different couriers, whereas PIO only have access to a very limited amount of data. Right? So this is like when we launch services in a new city or onboard a new courier to our platform, then we should consider using our approach. Right? However, as we collect more and more data from each person, the performance of PIO improves, and eventually it becomes slightly better than our approach. Right? So I guess the takeaway here is that there might be some benefit to switch to personalization strategy at some point, but whether or not we should make that change is case dependent, because first of all, the difference is not that big. And second, this PIO strategy have higher overhead. We have to maintain one model for each person. And in our case, we only have one model for everybody. So that's definitely much, much lower cost. Okay.
Sorry, what if you keep decreasing 10 trips?
Yeah, that's a good point. Yeah, that's a good point. So I don't have it here because I just finished the experiment yesterday, but the curve is not too different from here. The marginal benefits is pretty small. Okay, so that's all I have to show today. And to quickly wrap up, in this paper, motivated by a real-world routing problem, we propose a new inverse optimization pipeline to improve the alignment between my recommendation and human perception. Right? And to make this possible, I propose a new approach to construct uncertainty sets based on decision data, which has never been done in the literature, and we use some conformal prediction idea to achieve this. We show some theoretical results about the quality of my sets, the quality of my recommendations. We show very good performance using real and synthetic data. What I didn't have time to talk about today is computational efficiency. So compared to the existing pipeline, we have to solve additional calibration problem and also a more challenging, robust optimization problem. So in the paper, we actually have a bunch of methods to accelerate the entire pipeline. It doesn't really take too much time compared to the traditional one. And if you're interested in that, I'll be very happy to talk more about it offline. And I want to finish the talk with, I think, the most important message I want to convey today, which is, I think it's very important to consider human behavior when we think about making recommendation using algorithms. Right? So we have made tremendous progress in the past decades. We have the best machine learning model optimization algorithms that outperform human beings on some important benchmarks. But whether or not we can realize this benefit in practice depends on human behavior, depends on how they interact with the algorithms. And I think conformal prediction will continue to play a very important role along this direction, because when we talk about human behavior, there's always uncertainty, and the conformal prediction is a very elegant way to quantify that. And yeah, this is something I've been thinking about for a while, and I continue to feel excited about it. I encourage everybody to think more about problems along this direction, and I will be happy to talk more about this in the future. Okay, so yeah, with that, I'll stop here. Thanks for everybody for the attention.
Well, thanks, Bo. Great talk, great slides. And thanks, by the way, for your patience with my previous questions. I have one last question. Other than this computational issue that you mentioned, what do you think may be other limitations of this framework?
So I don't think those are limitations. It's more like some opportunity we can explore in the future. So first of all, right now, we only focus on objective functions that are linear in the unknown parameters. So it will be interesting to generalize this to other cases. There could be some work that we have to do. And also, I think, I think this is related to one of the questions that you asked previously. Our coverage guarantee is marginal. It will be interesting to think about how to incorporate some contextual things into this framework and then derive some contextual coverage guarantees. Yeah, that's the two things on the top of my head. Yeah.
But so you think that this method will work equally well even if you apply it on problems that have much more complex forward models?
And honestly, I don't know this for sure. We have to see the experiments, but I think I'm confident about this. Okay. Yeah. Yeah. Mm-hmm.
Great. Well, wonderful. Thank you again for the very interesting presentation. The recording will be available on the channel, and people if you have like audience who will watch the recording, please feel free to reach out to Bo if you have any questions. I will make sure to put a link to your LinkedIn in the comments section of the video.
Thank you so much.
With that, we can end this call. Thank you.
Thank you.
Have a nice evening. Bye.
Yeah.